In section 1.7, we're going to be talking about parametric curves. And the basic idea is going to be in two-dimensional space. Let's say you have x and y here, and let's say you have some curve that is going through space. And not only do you have some curve going through space, but there is a particular direction associated with this curve. So you can think about a particle moving along this curve and moving in a particular direction. And we normally call a curve like this C. So suppose we have a situation like this, where we have a particle moving along a particular path or curve in a particular direction. Well, you can think about that particle then moving along this curve and being in different positions for different times. So, for example, if you start at a point here and say this is when t is equal to 0, well then where is it at 1 second? Where is it at 2 seconds? Where is it at 3 seconds? And so on. And if we can put that in sort of an analytic form, then we have what we call the parametric equations for this curve. So in other words, if we can say that the position at some point here, so this is going to be at some point in time, well, it's going to have some coordinates x and y. And if the x coordinate of the position of the particle at some point t, at some amount of time t after t equals 0 is our starting point, if that can be some function of t, we'll call it f. And then our y coordinate can also be written as some function of t, which we'll call g in this case to stay consistent with the book. What we have is a set then of parametric equations. And this set of parametric equations then tells us where our particle is along this curve at any time t. And you can think of it then as an ordered pair x, y, or f of t, comma g of t. And then if we do have a parameterization, that we call parameterization, in other words, we can say where the particle is at any time t by a couple of functions, then we do call C a parametric curve. So if we can parameterize this curve, we call it a parametric curve. T in this case is the parameter. And we do use T because in most applications where we do parameterize a curve and look at parametric equations, the T does stand for time. It doesn't necessarily have to stand for time, but it usually does, and that's why we use t in most cases for our parameter. Now, one thing we can always do is parameterize a function y equals f of x. If we can have some function y equals f of x, we can parameterize that, and we can do it very simply by letting x be equal to, well, we need it to be a function of t. Let's just let x be equal to t. So the identity, well, so it's just x is whatever t is, and y then is just going to be, in this case, f of t. Now I'm using f here. This f is different than the f we talked about as a general function for our x position of our parametric curve. So if in general we have y is equal to some function f of x, then we can parameterize that always by just letting x be equal to our parameter t, and then y, we just basically change the variable. For example, if you look at y equals x squared, we know what the graph of that looks like. We've looked at it a couple times already this semester, and it should be familiar to you in any event. We have a parabola there. Well, let's look at the parameterization of this thing with respect to t. If we let x be t and then let y be, well, in place of x squared we'll write t squared. Well, that's going to be a parameterization of this thing. At t equals 0, what do we have? Well, we're going to have x is 0 and y is 0. So when t is equal to 0, we have this point right here at the origin 0, 0. When t is equal to 1, we have 1 comma 1 squared. So we have the point 1, 1. When t is equal to 1. When t is equal to 2, we have 2 comma 2 squared, which is 4. 2, 3, 4. And so we're at this point right here when t is equal to 2. Now, if we can go into negative time, if we can go into negative territory for t, if you have, say, a flux capacitor, a DeLorean, and there's a lightning storm in the forecast, well, at negative 1, x is negative 1, y is negative 1 squared, that's positive 1. So here's t equals negative 1. If you let t go to negative 2, negative 2 and negative 2 squared is positive 4, so you'd be up here. In other words, you get the exact same curve, only we have a little bit more information about it. We have a parameterized version of this parabola, and we can see where our particle is if we think about this particle moving along this curve as time goes by. In negative time, negative 2 seconds, negative 1 second, 0 seconds, 1 second, 2 seconds. Notice that it covers a lot more space between second 1 and second 2 than it does between second 0 and second 1. It's kind of interesting. So, there are ways to graph these. Using graphing programs, in particular that WinPlot program that we talked about, WINPLOT, will work very well for graphing parametric. What you need to do is, let's close this up so you can see how we get to it from scratch. If you open up the two-dimensional window and go to Equations, and then the second one down, you can't quite see it there, Equations, and then you can see Parametric, and that'll open up a window where you can put in the function for x and the function for g. Let's look at the function we just looked at, where x was equal to t, and y, our g of t function, was equal to t squared. And let's go ahead and hit the graph button and see what happens. Well, we get the half of that parabola, only the right half of that. Why is that? Well, if you look again at our function, you can see that our low t was 0 and our high t is 6.28, that's 2 pi. If we take our low t back to negative 2 pi, or negative whatever, now we have t's in negative territory. Now we get the first part of the left half of this parabola, and then you can think about it again, moving along this curve from left to right as time goes by along this parabola. And that's why a lot of times with our parametric curves, like that first example we looked at, we'll put arrows on that curve so we are clear which way a particle moves as time goes by. And we would want to do the same thing back here on this parabola, indicate that we're moving along the parabola in that direction. So with that being said, let's look at a few examples. Most of the homework problems that you have are going to be doing this very thing here, where you're asked to eliminate the parameter to find a Cartesian equation for the curve. So let's start off with number 6, and we'll look at this one. We have two functions for x and y, so we have a parameterization. X equals 1 plus 3t, and y is equal to 2 minus t squared. What we want to be able to do is write this as a single function y as a function of x. Now, are we sure we're going to be able to do that? Well, that's going to depend on whether or not we have a function that passes the vertical line test. Notice we don't have to have a vertical line function of our graph to be able to parameterize a curve. We'll see more examples of that as we go. But let's see, let's delete that one and delete that one. Let's try another one here. Let's put the curve that we're just looking at. X was equal to, I think, 1 plus 3t. So that was our function for x, and our function for y was 2 minus t squared. So let's get an idea of what this looks like. And you can see, let's see, that's for values of t going from 0 to 2 pi. Let's go from negative 2 pi to 2 pi. It looks like this is a function. You can see it passes the vertical line test, so we should be able to eliminate the parameter and represent this curve as a function y equals f of x, y as a function of x. Well, usually the easiest way to do that is going to be to solve for t in one of our equations, usually the x equation. If I have x equals 1 plus 3t and I can solve this for t, which isn't too bad to do, x minus 1 equals a positive 3t. Dividing both sides by 3, I get that t is equal to x minus 1 over 3. And then what I'm going to do is I'm going to substitute that x minus 1 over 3 in for t. And so now I have that y is equal to 2 minus, in place of t we're putting x minus 1 over 3 quantity squared. So y now is completely dependent on our independent variable x. We have written y as a function of x. Let's check that, and let's look at an explicit function and see if we type that in. It was 2 minus the quantity of x minus 1 over 3. Let's see, so we're going to need x minus 1 in parentheses, another set right there, and then all that squared. And if we hit graph, you can see that yellow curve went directly over the green curve. So this is just as a regular function, y as a function of x, and we have eliminated the parameter from the original parametric curve. So that is the correct function and what we were looking for this particular problem number 6. Let's try another couple of these. Let's take a look at number 8, where we have x is equal to t squared and y is equal to t cubed. The same directions that we had for number 6. We want to eliminate the parameter. So what we're going to do then is, well, you'll notice that, let's see, if we solve x equals t squared for t, we actually have two possibilities. T is equal to plus or minus x. And so that seems to indicate that we can't really do it the way we did before. And if we look at a table of values here for t, x, and y, and kind of get a picture of the graph of what this thing looks like. Remember, x is going to be the t value squared, y the t value cubed. And just trying some different values for t, like 0, 1, 2, maybe negative 1 and negative 2. Well, when x is equal to 0, t squared is 0, t cubed is 0. So we're at the point 0, 0 at time t equals 0. 1 second after that, we're at the point 1, comma 1. t squared is 1, t cubed is 1. 2 squared is 4, 2 to the third is 8. So at 2 seconds we're at the point 4 comma 8. If we go into negative time, negative 1 squared is positive 1, negative 1 cubed is negative 1, and negative 2 for t gives us a positive 4 for x and negative 8 for y. Well, sketching a picture of what this graph looks like then, we can see that, let's see, we need to go 1, 2, 3, 4 for x, and we need to go 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Plotting some points at t equals 0, we're at the point 0, 0. 1 second, we're at 1, 1. At 2 seconds, we're at 4, 8, so we're up here. In negative time, negative 1, we're at the point 1, negative 1, so 1, negative 1's right here. And 4, negative 8 at time t equals negative 2, which is down here. So connecting these points here, you can see that we actually do not have a function. We can't write this as a function y equals f of x because this graph does not pass the vertical line test. You can see there are numerous vertical lines that go through the graph at more than one point, which goes along with the fact that we couldn't solve this for t. Now, we can, however, solve this equation for t, y equals t cubed, because you can see what happens. If we tried to solve this for t, what we would get is that t is equal to plus or minus the square root of x. And so we can't solve t explicitly in terms of x. It's either the positive or the negative square root. However, we can solve this for t. T is equal to the cubed root of y. So since I can write t as the cubed root of y, what I'm going to do is substitute that in for t in my formula for x. So I got all kinds of stuff going on here, but I can replace the t with the cube root of y, so I have the cube root of y squared, or x is equal to, we could write this as y to the, well, it's the cube root is 1/3, so I have y to the 1/3 squared, or x is equal to y to the 2/3. So although I couldn't write y as a function of x because my graph did not pass the vertical line test, I can write x as a function of y, and thus eliminate the parameter in that fashion. Let's go ahead and look at number 10. Notice in number 10 we have a set of parametric equations, x equals 4 cosine theta, y equals 5 sine theta, and theta is bound between negative pi over 2 and pi over 2. So we do have some bounds on our parameter. Our parameter in this case is theta. We said usually it's t, but it does not necessarily always have to be t. Let's go ahead and see if we can plot just a couple of points here to get an idea of what this is going to look like. So here's going to be our 4 cosine of theta, and y will be our 5 sine of theta. This is our y value here. And let's just try some major angles, some major values for theta. We're starting at theta equals negative pi over 2, so let's start there here. When theta is negative pi over 2, let's see the cosine of negative pi over 2. I want you guys to know the sines and cosines of major angles. Cosine of negative pi over 2, that's cosine, well, the cosine is the x value, that's 0. So that's going to be 4 times 0, which is 0. Now the sine of negative pi over 2 is negative 1. Since the sine is the y value, negative pi over 2 is straight down the negative y-axis. So it's 5 times negative 1, or negative 5. Now what happens when theta is equal to 0? Well, the cosine of 0, remember cosine is the x value on the unit circle. If 0 is straight out the positive x-axis, so the x value is 1 there. 4 times 1 is 4. Sine of 0 is 0. 5 times 0 is 0. And let's go then to our upper limit of our parameter pi over 2. Cosine of pi over 2 is 0, just like the cosine of negative pi over 2 was 0. The sine of pi over 2 is 1. 5 times 1 is 5. We only have 3 points, but it's going to give us a good idea of what the graph of this looks like. We're going to have, let's see, we have to go out to 4 on the x-axis, and positive 5 and negative 5. Let's see, this should be a 5 right here, shouldn't it? Let's get rid of that. And we had the sine of pi over 2 is 1. 1 times 5 is 5. Let's see if I can get the, there we go. Alright, so 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 in the negative direction, x here, y here. So at negative pi over 2, we were at 0, negative 5, which is going to be this point down here. And then as theta increased, our parameter went from negative pi over 2 to 0. Our function went from, our curve went from 0, negative 5 to 4, comma 0 right here. So it kind of swept out in this direction. And then we went from, as theta went from 0 to pi over 2, we went from 4, 0 to 0, 5. So we went up here. Whoops. So let's try that again. Get a nice smooth curve. What we have actually here is half of an ellipse. We have the right half of an ellipse. And notice that we also have a particular direction that we're going here. As theta increases, as our parameter increases, we're moving that way along our curve. Now, in order to eliminate the parameter here, you can see we don't have a function, y as a function of x. We don't pass the vertical line test. But what we can do is we can use the fact that cosine squared, actually let me write this so you can see it here. We can use the fact that cosine squared of theta plus sine squared of theta equals 1. This is a very important trig identity, and you'll use it a lot throughout your calculus careers. Cosine squared theta plus sine squared theta is equal to 1. So what I'm going to do is solve each of these for cosine and sine. What I get is that x over 4 is the cosine of theta, y over 5 is the sine of theta. And since x over 4 is the same as cosine, y over 5 is the same as sine, we can write that in place of cosine we had x over 4 squared, plus in place of sine we had y over 5 squared. All has to come out to be equal to 1. Now you recognize this, x squared over 4 squared plus y squared over 25 or 5 squared. Hopefully you'll recognize this as the equation of an ellipse. This is one of the conic sections, an ellipse that intercepts the x-axis at positive and negative 4, intercepts the y-axis at positive and negative 5, which is exactly what we have here. Now we do have to restrict it. We only want the part of the curve that's showing for us. The part of the curve that was showing for us was restricted to the right half of the ellipse because of the limits on our parameter. And so we want to make sure we have the appropriate limits on our x or y value. Notice that this is just where x is equal to 0 or larger. So we want x to be greater than or equal to 0 as the limits on x, because we're just in the positive territory for x here, to make sure we just get the right half of this parameter. If we take a look at this in wind plot, if we sketch this graph out, we had 4 cosine. Now we have to put t in here instead of theta, but that's okay. There's no t is still the parameter when we put it into this program. And what do we get here? Well, we get the whole ellipse. Now, but notice though, the limits on our parameter, they were from 0 to 2 pi. Let's put in what we wanted, negative pi over 2 to pi over 2. There we go. There's the right half of that ellipse. We can't quite see the top and bottom half. We don't have quite. There we go. There it is. So going from negative 0, negative 5 to 4, 0 to 0, positive 5. But again, if we do the entire 0 to 2 pi, that's going to take us all the way around. That's going to start here and go this direction from 0 to 2 pi back to this spot right here. And that's going to be it for this video. We'll do a couple more examples and look at a couple more things from 1.7 in the second video.